Okay, so now we will start talking about contributions to different observables that come from higher order corrections in quantum field theory, and these will involve Feynman diagrams that contain loops. Okay, so that's the plan, and we should understand that the real content of quantum field theory resides in these loop diagrams. So let me first define what a loop diagram is. So a diagram that contains one or more loops. That contains one or more loops. We have seen examples of such diagrams. For example, if you are looking at a two-point function in 5-4 theory, this is a possible diagram. Okay, this is a two-loop diagram. This is a one-loop diagram. And if you are looking at two-point functions, this is one of the contributions which is at one loop, and so forth. Okay. So this is what we call a loop diagram, and then we have something called tree diagram. Tree diagrams are those that do not contain loops. Okay, for example, you can look at this. This is in 5-4 theory again. 1, 2, 3, 4. Sorry. This is a tree diagram. Okay. And if you put more lines here, it still remains a tree diagram. Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8. Okay, this has 8 external lines, so it contributes to a Green's function with 8 fields. And this is a tree diagram because it does not contain any loops. Okay. Now, the reason I am interested in loop diagrams is because if you are interested in some observable, let's say cross section. Okay, and if you calculate cross section using only the lowest order diagrams, then the result that you get, okay, it is not going to match with experiments, because there can be a big difference between this experimental outcome and what you are predicting from theory, not because your theory is not describing your experimental result correctly, meaning you do have a right theory, but because you have not included quantum field theoretic corrections into your calculation. Okay, I will talk more about this later, and I will show you also the example of Higgs production, where it is very much clear that if we had not gone to higher orders in the calculation, okay, then we would have easily misunderstood the 2-photon peak that was observed in the experiment. Okay, people would have wrongly concluded that what we are seeing in experiment is some new physics signal and not standard model physics. Okay, so it's important that one gets the contributions of loops into the calculations. Okay, otherwise predictions are usually far from reality. There is also another reason that if you do not consider loops, then some processes will appear to be impossible, which in fact can occur. For example, if you look at scattering of 2 photons, we have not done this, we have done only scalar theory, but I am giving you an example. So if you look at the scattering of two photons, these are represented by these wavy lines in literature. Now there is no vertex which connects two photon lines, but there is a vertex which is like this. So this is some fermionic line and that's a photon. Okay, that vertex exists in QED, quantum electrodynamics. Okay. So if you want to scatter a photon from another photon, it looks like it is impossible at tree level. Okay, it's not possible. But if you include this vertex and make a loop, this is a fermionic loop. Using this vertex, I can draw this Feynman diagram. Okay, where here you have fermionic propagator. This could be an electron. Okay, then you see that two photons can scatter non-trivially to give two photons in the final state that are going in different, are having momenta which are different from the incoming momenta. Let's say P1 and P2 are the incoming momenta, and Q1 and Q2 are outgoing momenta. Okay, then this scattering can give you Q1 and Q2 being different from P1 and P2. Okay, but this process cannot occur at lower order than this. You have to involve a loop. Okay, so that's another reason why we need to consider these loop diagrams as well. Okay, so we are going to see that there is a lot of trouble the moment one wants to include these loop diagrams, but fortunately the machinery to deal with these things is well developed, and that's what I'm going to describe in this. I will start describing in this lecture today. Okay. Okay. So let's look at one example. Okay, this is the 2-point function. Let's represent the loop momentum by L. We have already learned in the first course that when you have loops, the number of loop momenta running in the loops is equal to the number of loops. So L is undetermined. It is not fixed by the external momenta. Okay, it remains undetermined and we have to integrate over it. So if P1 and P2 enter, okay, they enter it at this vertex as P1 plus P2. Okay, that is what enters here. Okay, and L goes out in this direction, and here you will have P1 plus P2 minus L. Okay. So if you take it backwards, it will be in this direction minus P1 minus P2 plus L, and this will be minus L, so that at this vertex the sum of all momenta entering is equal to 0. Okay. So let me write down the expression. It is d4L over 2 pi to the 4. Okay, I'm just writing the loop integral over L square minus M square plus I epsilon okay, and then we have to do this loop integral where d4L is dl0 and dl1, dl2, dl3. Okay, and you see that the poles, if you do not take into account this I epsilon, then you get poles at poles on the real axis. So you should view this as an integral over L0 in the complex plane. Okay, and here this is L0 square. So L0 square minus L square minus M square. Okay, so you see that when L0 is L square plus M square plus minus square root of this, then you have a pole on the real axis. Okay, and the integration contour also goes from minus infinity to plus infinity along the real axis. So this is the integration contour, and then you have these poles sitting on the contour, so that the integral is ill-defined. It is not defined if you have poles sitting on the contour, but then you are safe because you have I epsilon, okay, that takes the poles off the contour. Okay, and we are going to see how exactly these I epsilons help us in having these integrals well defined. Okay, so that's what I'm going to show you. So let's take a generic case, not necessarily a 4-point function, but any one loop diagram of this kind. So I'll just so here you have, even if you have several lines, okay, depending on whatever theory you are looking at. So here 1, 2, 3, 4, 5, 6. So you have a 6-point vertex. So clearly we are looking at a theory in which you have 5 to the 6 term in the Lagrangian. Okay, and here let's say 5, 4. So you have both such vertices. And if you have momentum P1, P2, P3, P4 here, then as I said in this case, the momentum that enters in here is the sum of all these. So let me define P to be, okay, so all these sum enters, and similarly here you will have the corresponding sum. But anyway, whatever goes in has to come out. So I will, instead of putting all these external legs, I will draw this simply as, okay, but this does not necessarily mean that I am looking at a phi cube theory. It could be coming from phi cube theory, but this line stands for all these lines and carries the momentum P, okay, which is sum over Pi. And if this is L, then it says this one is P minus L. Okay, so this is the diagram I want to look at. This is a particular one loop diagram. Now if you look at this, the corresponding integral is already, I have written here. Let me write it on the next page. An integral is d4L, and remember that the limits run from minus infinity to plus infinity. Okay. Now I want to look at this integral and pay attention to those configurations for which L0, L1, L2 and L3, they are all large. Okay, they take very large values because the integral runs up to infinity, so this is something, these configurations will appear. And I also want to look at those configurations, or I want to add a qualification that L square is also large. You see, because we are in Minkowskian space, L square is L0 square minus L vector square. I will put it like this, L1. So instead of this, I'll put here. So L1, L0 square minus L1 square minus L2 square minus L3 square. So even if all these components are large, L0, L1, L2 and L3, it's possible that the difference, this difference is not large. Okay, so it's possible that L square is not large, but I want to look at those configurations for which L square is also large. In that case, I want to know the behavior of this integral. How does it behave when all the components are large, such that L square is also large? So in that case, this m square is irrelevant. This I epsilon is also irrelevant. Okay. This m square I can drop. This p also I can drop in comparison to L, because p is some fixed for momentum, and I am talking about L being very large, so p in comparison to a very large momentum can be dropped. Okay. So this integral I behaves as d4L 1 over L square times 1 over L square. Okay, which is, so you do the angular integrals. Okay, I'm being very not being very careful right now, but all I'm doing is counting powers of L. So this is dl L cube. Okay, that's d4L, and then you have 1 over L power 4, okay, which is dl over L. Okay, and I'm interested in only the upper limit infinity. So to see clearly how things behave, let me put a cutoff, lambda, and then I should take lambda to infinity. When I take lambda to infinity, I am looking at again this integral in the large momentum limit. So how does this behave? dl over L is log of lambda, log of L, and if I put the upper limit, it gives you log of lambda. Okay, I'm not worried about what is on the lower limit, because I'm not evaluating this integral. All I'm doing is just trying to figure out the way this integral behaves in in the limit of large L. Okay, so I am concerned only with the upper limit of L, which is lambda right now, not the lower limit. So you see that now this is log of lambda, meaning as I take lambda to be very large, this diverges logarithmically. So we have a logarithmic divergence. Okay, so this integral is divergent, and such divergences are called ultraviolet divergences. Okay, and I will discuss in more detail about ultraviolet divergences later, but right now my interest is not in this ultraviolet divergence, but rather looking at this integral, that whether this integral is well defined or not. Okay, because you have these poles which are close to the contour, and these I epsilons are helping us, but we have to see that indeed whether they are really making the integrals well defined. Okay, so what I'll do is, I will not consider this integral because this is ultraviolet divergent, but I will look at an integral which has the same propagators, so everything remains the same, but I change the d4L to d2L. So I go to a lower dimension. Instead of working in 4 dimensions, I will work in 2 dimensions. Okay, then this d4L gets replaced by d2l, and this is helpful because as far as this divergence is concerned, this goes away. So you see here the power counting was that you have 4 powers of L in the numerator, 4 powers of L in the denominator, and that gives you a logarithmic divergence. So if I have only d2L here, it will be 2 powers in the numerator and 4 powers in the denominator, and that is convergent. Okay, so that integral will converge for large lambda. Okay, so I will get rid of ultraviolet divergences, and I can then focus on the issues that I am interested in. So that's what I am going to do. So I will define a new integral I tilde, okay, which is d2L, L is for loop momentum, 2 pi square. I have also changed this factor, 2 pi to the 4 to 2 pi to the 2, okay, and 1 over L square minus M square plus I epsilon times, I have dropped the factors of I should have kept actually. Okay, let's drop it. Let's drop them from here as well. Okay, now one thing I should have mentioned here is that this p square is not necessarily equal to m square. Okay, if it was a particle, then if p square was on shell momentum, then it would have been equal to m square, the p square. But here p is sum of all these momenta, which let's say they are on shell. So p1 square is m square, p2 square is m square, and so forth. Then p1 plus p2 plus p3 plus p4, that's square of the sum will not necessarily be equal to m square. So you don't have that condition. Okay, so I will not make use of that relation, which is only true for on-shell particles. Where I was, yeah. Okay, so I want to look at this integral I tilde. First, let's look at the arguments of this integral, meaning of what quantities this integral is a function of. So L is integrated over, so this quantity, this integral cannot depend on L because L is dummy. It can depend on m square, okay, because there is this constant that appears. Okay. Then it can also depend on P. Okay, but you see this integral is made up of Lorentz invariant objects. L square is Lorentz invariant, m square is Lorentz invariant, L minus P square is Lorentz invariant, d4L or d2L. If it was d4L, that would have been Lorentz invariant. But if it is two-dimensional space, this is also Lorentz invariant. So this integral is only a function of the vector p, okay, p mu. But because the integral is Lorentz invariant, it cannot be a function of p mu. It can only be a function of p square. Okay, there is no other possibility. So it has to be a function of p square and m square. See, if you had this integral in which you had some other vector also appearing, okay, let's say you had L minus P1 minus P2, or let's say L minus P minus K, okay, where K is also some external momentum. Then you will have P dot K also available to you. This is also a Lorentz invariant quantity, and K square is also a Lorentz invariant quantity. So all these things would also appear in I tilde if you had k also appearing in this integral. But now because you have only p, and the only invariant you can construct using p is p square, and that's why I tilde will be a function of p square and m square. Okay. So now we want to look at the evaluation of this integral I tilde. So for that, I'm going to introduce a technique which is called Feynman parameterization. So if you have 1 over A1 times 1 over A2, okay, where here, for example, in our present case, A1 is L square minus M square plus I epsilon, and A2 is L minus E square minus M square plus I epsilon. Okay. So the technique is you can combine these A1 and A2 like this. So we introduce a parameter called Feynman parameter dx, and the integral runs from 0 to 1. And the denominators combine in this fashion. X A1 plus 1 minus X A2, and here you will have a square. You have A1, A2, so two denominators, so there is a square here. Okay. And I will encourage you to prove this relation, that this is indeed true, but I will I will just assume that this is to be true, and I will work with it. Okay, so let's look at this integral now. So A1 are defined to be L square minus M square plus I epsilon, and A2 to be L minus P square minus M square plus I epsilon. So the denominator is X A1 plus 1 minus X A2, okay, and if you calculate this, you are going to get L square plus 1 minus X P square minus 2 1 minus X L dot P minus M square plus I epsilon. Okay, I am keeping carefully these I epsilons. Okay, check this. Check that you get this. That's an exercise. Now, what I want to do is, I want to complete the square for L. So here you have a linear term in L. Okay, that's a quadratic term. So I want to complete the square. So let me write down the following. I'm looking at this one and this one right now. So I write this. I write L mu. Okay, L mu square. L mu will be L square. So that will generate this term. And here you have minus 1 minus X P mu. Okay. So when I square this, it generates L square, which is here. It generates a square of this, which I should subtract. So it is 1 minus X square P square. And then it generates the product of these two terms with a factor of 2, which is what you have here, right? Minus 2, 1 minus X, L mu, P mu, which is L dot P. So that is this term. And I have removed the constant term. Now let's include this one. This is this. Okay, so I have completed the square for L. Okay, which is same as plus x1 minus x p square minus m square plus epsilon. Okay, so this is what now sits in the denominator. Okay, so what I will do now is define k mu to be L mu minus 1 minus x p mu. Okay, so what do we have then? We have d2k is equal to d2l. So I will now express I tilde in terms of the variable k mu rather than L mu. So I tilde p square m square is equal to integral 0 to 1 dx, and I should have mentioned x is called Feynman parameter. It's a Feynman parameter. Now you have d2k over 2 pi square times k square because this has been defined as k, so that's k square, plus x1 minus x p square minus m square plus epsilon, and then you have a square of this. Okay, that square comes because you have a square here. Okay, and that square here is really because you have product of two functions, 1 over a1 and 1 over a2. That is why you get a square there. Okay, so now we are in this space, two-dimensional space, k0, k1. Okay, but I will keep writing this as vector k. Okay, because you could have also, instead of looking I tilde, the one I am looking at, you could have looked at d cube L, for example. That would also have been convergent, right? Because if you have 3 powers here and 4 powers below, that converges. So I am just keeping the notation more general. Instead, in fact, I could have also looked at, instead of d2l, dnl, where n is anything, 2, 3 or whatever. So I will just write k instead of k1. But you understand that in 2 dimensions, the time component is k0 and then you are left with only one component. Okay. But if you don't like what I am doing, you write only k1. So k square, the denominator is k0 square minus k vector square okay. So where are the poles? So this is an integral, and the integrand has some poles. Okay, it vanishes at some values, and we are asking what are those values at which this integrand vanishes, and the poles are at, and of course I am looking at things in k0 plane. Okay, so k0 is equal to plus minus okay, these are the locations of the poles. Now note that x is running from 0 to 1. So x is always positive, which means, x is always positive, of course, but also smaller than 1. So this x is always positive, and this factor 1 minus x is always positive, which means x times 1 minus x is always positive. Okay. But here the sign is not fixed because it depends on what the value of k square is and what's the value of p square, whether it's positive or negative. Okay. So what I'll do is I'll take the case p square less than 0, meaning p is space-like. Okay, just choose this configuration. Other p square configurations are also present. You can work for those also, but I want to look at the case when p square is less than 0. Okay, and see what happens then. Now, if I take p square to be less than 0 or negative, space-like, then this term minus x times 1 minus x p square, that becomes positive. Okay, it becomes positive. So let me define p square to be minus capital P square, where capital P square is positive. Okay, so this minus sign takes care of the fact that p square is space-like. So k0, the poles are at plus x minus x capital P square plus m square minus epsilon. So this is the place where the poles are. Okay, and let me draw the k0 plane. So where are the poles? On the plus side, you have here, because of this minus I epsilon, you have here a pole which is and on this side you have here, because minus makes that I epsilon plus. And this is our integration contour, because the integral over dk0 runs from minus infinity to plus infinity. Okay, so poles are located at these places. Okay. Now what I can do is I can use Cauchy's theorem. Okay, and do the following. So you have this situation where the poles are located like this, and the contour integration is this. Let me call the integration contour as gamma. You can put a semicircle which is infinite in length, infinite semicircle here. Okay, and doing so, then you are picking up this pole. Or if you were to close it below, then you are picking up this pole. Now what I'll do is, see this contour, this encloses only this pole, not the other one. And similarly here, this contour encloses only this pole, not the other one. Okay. And if the contribution from semicircle goes to 0, then you are allowed to close the contour like this. Okay. So let's look at this one. Here, I can do the following. What happened? Oops. Okay. So here, I can just rotate this contour. See, as long as I am not crossing any poles, I am allowed to deform the contour. Okay, if the poles that are enclosed within the contour, they remain unchanged, using Cauchy's theorem, I can deform the contour without changing the integral. So I will just, what I'll do is I'll rotate it, and this I will take to here. Okay. So then the contour becomes, so take the x-axis and rotate by 90 degree clockwise. Sorry, not just a second, hold on. Yeah, you rotate it 90 degree counterclockwise. Okay, and doing so, we are in this situation, and which is fine because I still enclose the same poles, and no new pole has entered in this region. Okay, so I can deform the contour this way, and similarly here I could have, if you close this way, then again deforming is allowed. Okay, because then it becomes okay. So you see, you enclose exactly the same poles and no new poles are in this region. So these deformations are allowed using Cauchy's theorem. Okay, so instead of evaluating along the x-axis, along the real k0 axis, I can evaluate along this imaginary k0 axis. Okay, that is the this is what is called Wick rotation. Okay. Okay, so we will do this Wick rotation, and we should also note that this rotation from real axis to the imaginary axis is possible because of the way these poles are placed here. Okay, because these poles are not hindering the rotation of this axis, so we can do this. But if, and that is also due to the fact that we are looking at space like p square. Okay, so because we chose p square to be space like, these poles were coming out to be located at these places, which allows us to do a Wick rotation. But if you take p square to be positive, okay, in general you will not get an arrangement which allows you to do a Wick rotation. Okay, so that is why we are going to always look at space like case, space like p square. Okay, good. Now that our integration is along this imaginary axis, imaginary k0 axis, I will define k2 to be minus I k 0. So let me explain this notation. So you are working in k0, k1 plane. Okay, but now this k0 I am writing as I k 2, and this is k1. Okay, so 0 1 has become 1, and then this has become 2. Okay, if I had taken, instead of 2 dimensions like here d2k, if I had taken d3k, then it would have been k0, k1 and k2. Okay, 3-dimensional, and then the notation would have been, in this case, when I have done the Wick rotation, after that I would have called this as I k3, so that I have k1, k2 and k3. Okay, these will be the variables then. So that's a nomenclature. Okay, so sorry, that's the notation. So I have defined this, and with this definition the integral becomes integral over the Feynman parameter x dk1 and then dk2. The 0 thing has become dk0 has become dk2 over 2 pi square, and then you have 1 over minus 1 square times k1 square plus k2 square plus x1 minus x p square, where capital P square is positive, plus m square minus I epsilon square. Okay, and note that k2 is real, right? Because k0 is imaginary, because we are doing integral over the imaginary axis. See here this is k0 plane. Okay, I have turned the contour integration from this to this. Now k0 takes imaginary values on this imaginary axis, but because I have multiplied k0 with minus I, this has become, k2 is a real number. Okay, so k2 takes only real values, k1 also takes only real values. So this k1 square, k2 square, these are all positive numbers. P square is positive, x times 1 minus x is positive, as I argued earlier, m square is positive. So everything in the denominator is positive. Okay, so it doesn't become 0 because it's positive. So there is no need of I epsilon. Okay, you can drop it. Okay, and then of course you have this this square also. Okay, we don't need this, so I will just remove it. Okay, good. So this is an integral that we need to do. We can do the angular integral first. That's easy because your integrand does not depend on angles. It is just depending on k1 square plus k2 square. So it's easy to do the angular integral. dk1 dk2, this is equal to, see we are doing in this plane, k1, k2 plane, and this angular integral will give you 2 pi times k dk, where k is now the magnitude of k1 square plus k2 square square root. That is what is k. So this is, let's call it k1, k2, and this is k. Okay. So I tilde p square m square is equal to 1 over 2 pi 0 to 1 dx 0 to infinity dk. This is the radial integral. Okay, and in angular integral I have done, I have to now do the radial integral. Okay, so radial integral is dk, k dk, so that k is here, over the denominator that I had written earlier, which now becomes k square plus okay, this is what you have. Now if you integrate this, you'll get the following. Okay, so this is what we get, and we see that this is, because you see p square is positive, m square is positive, so what you have in the square root is larger than 1. Okay, so subtraction from 1 will still give you something which is positive. So, and denominator is also positive, so log of a positive number, so that's positive. Here there is a square root of a positive object, which is fine. So this is an analytic function of p square, okay, capital P square. Now I can analytically continue this to, this is still for but I can continue this to all of complex plane. Okay, so I am treating p square as complex, okay, but I have removed this restriction of p square being negative. Sorry. Okay, this is for any p square. Okay, that's the continuation, because this expression is, I can put a minus here and make it p square, and which is valid for all p square less than 0. Okay, I can then continue for all p square. But then I see that this I tilde, which is the continuation of this I tilde, I should have used a different symbol, but it's okay. Okay, this analytically continued function, okay, has branch cuts. Okay, and where is the branch cut? The branch cut starts at e square equal to 4m square. Okay. Check that this is indeed the place where the branch cut starts. So you know the analytic structure of where the branch cut starts for a square root. Okay, so you can look at square root of z. Okay. You know where the branch points are for square root of z. Then you also have log. You also know where the logs has branch points. And then look at them together and convince yourself that the branch point is at 4m square. Okay, so that is the place where branch cut starts. Also, there is a 1 over p square, so it looks like there is a pole at p square equal to 0. Okay, in I tilde. But that's another exercise. Convince yourself, or maybe I'll show that to you. Okay. So in general, you have a 1 over p square at different branches of this function, but in the principal branch or in the physical sheet, you will not have a p square equal to 0 pole. Okay, and that is easy to check. You can also analyze this function and then convince yourself that p square equal to 0 is not a pole when you are in the physical sheet, but you can do it differently also. You can just look at I tilde and put p square equal to 0. And evaluate it. So this becomes 1 over 2 pi 0 to 1 dx dk 0 to infinity, and this is k over k square plus m square whole square. Okay, and you evaluate this and you will get 4 pi m square. I hope I made no mistakes, but this is what you should get. And clearly there is no singularity here, right? So I tilde of 0, which is p square equals 0, is a finite object, not a singular object. And that is why I made this claim that when p square equal to 0, there is no singularity. There is no pole at p square equal to 0. But that pole can be present in the other sheets. You see, this is a function which has a branch cut. So when you go to other branches, that pole may still be present. Okay, so that you have to carefully analyze and understand. Okay, so what we have seen is that if I take the external momentum of this Feynman diagram to be space-like, then I can do a Wick rotation. Okay, and the integral is clearly well defined because there are no poles on the integration contour. Okay, because this pole, when you take epsilon goes to 0, it goes here. It doesn't go here. Okay, so there's no issue of the integral being ill-defined because pole is not migrating to the contour. Okay, here it was other way around. The pole was actually going to the contour. So you see that taking space-like external momenta allows you a Wick rotation, and that gives you an integral that is well defined. Okay, and then you can do a analytic continuation to other values of p square, like here. Okay, and get the result for physical momenta. Because your physical momenta, if you are looking at a scattering process, okay, then these physical momenta will be time-like. Okay, they will not be space-like. So you can do a continuation to those momenta after Wick rotation. Okay, so I will next analyze the Feynman integrals without restricting to one loop, and I will arrive at the same conclusion that this whatever procedure I have outlined can be repeated there, which means that these Feynman integrals or these Green's functions are well defined, okay, for space-like external momenta, and then we can do analytic continuation. I'll make a side remark here. This p square equal to 4m square you have seen earlier at some point when we were talking about the spectral density, and I had given a remark that spectral density has a branch cut starting at 4m square, which is the threshold of creating two particle states. So you see p square is 2m whole square. Okay. If the external energy is such that it produces barely two particles at rest, then p square is 2m square. Okay, and this is the threshold of producing two particles, and this is what you're seeing here, that this 2-point function has a branch cut starting at 2m square. Okay, and it comes because of this integral here. So you see, when this p is such that the energy which you pump in is just sufficient to produce two particles at rest, each having mass m, then you have 2m square is 4m square, and that is why you have a branch cut starting at 4m square. Okay, this is what we had said earlier, and here you now see after an explicit integration. Okay, so we will continue this discussion in the next video.